Hey everyone. In this video, I want to share some insights on multimodal models and multimodal fusion. So we'll learn about how these models work, what are some strategies to implementing them, and why might we want to implement them. We'll also go through some applications of this particular strategy. So let's get right into it. So what does multimodal mean? Well, I think it's best to explain it with an example. And it turns out that humans are inherently multimodal. So when I'm trying to learn something, I find it better when I can intake information from multiple sources about that subject. For example, if I wanted to learn about the transformer architecture, some of the sources I would use are the official transformer paper, a couple of YouTube videos explaining the architecture, and a in-depth coding tutorial implementing the transformer in code. By taking in multiple sources of information and multiple types of information, I'm able to better understand the essence of the content. And I'm sure you can relate to this. But we're not just multimodal in the way we learn. The way we interact with others is multimodal too. Think back to your last conversation. Not only were you analyzing the other person's voice, but their pitch, tone, and body language all contribute to the demeanor of the conversation. That being said, a machine learning model can also benefit from integrating information from different modalities, giving it a comprehensive view of the subject or task. The process of fusing these different modalities so that a model can learn from them is called multimodal fusion. And models which utilize multimodal fusion are called multimodal models. Let's explore a use case of multimodal fusion. Device-directed speech detection, or DDSD, is the binary classification task of distinguishing between queries directed at a voice assistant versus side conversation or background speech. It's essentially how voice assistants can detect when you say, "Hey Siri" or "Hey Google." This is quite a challenging task, as the voice assistant has to distinguish between loud background noise and irrelevant conversations to isolate your specific directed invocation. One way to enhance the quality of the trigger word detection is to utilize both verbal and nonverbal cues. In addition to using verbal cues, such as the words that were said, the model can also utilize nonverbal cues, such as prosodic features. Now, what are prosodic features? Prosodic features are the way we say what we say, such as pitch, intonation, stress, and rhythm, and even visual cues if the model has access to them. For example, we tend to talk louder, slower, over-articulate, and avoid having stop words or speech fillers, such as and when we issue a command to a voice assistant. In other words, while the acoustic-based DDSD focuses on what was said, prosody-based DDSD focuses on how a query was said, and it can use those two modalities to predict the device directedness. Combining these different modalities of information enables the model to utilize verbal input as well as important nonverbal cues, leading to an enhanced trigger word detection. We'll touch on other applications of multimodal fusion throughout the article, but let's take some time to actually understand how the fusion process works in a machine learning system. Let's go over some strategies for multimodal fusion. Models can benefit immensely from integrating data from various modalities, but how and when the fusion is performed is crucial to the success of a multimodal model. The first step in understanding multimodal fusion is to understand embeddings. Different modalities, such as text and images, can be processed into a common representation, called an embedding. Essentially, an embedding is a super condensed, machine understandable list of numbers, which captures the essence of the source information. Embeddings enable models to reason about different modalities on the same semantic level. For example, an image of a cat wearing sunglasses can be converted into a 16-length embedding. And the sentence, "This cat is wearing sunglasses," can also be converted into a 16-length embedding. By comparing the embeddings, a trained model can then reason that these two pieces of information are similar. Here's a diagram here showing that different forms of data or different modalities of data can be converted to a common representation, which is a list of numbers or an embedding. Now let's tackle how we can actually combine the information from different modalities to enhance a model's predictive capabilities. There are four general strategies for multimodal fusion. Early fusion is when we fuse the modalities into a single representation at the input level, and then push the fused representation through a model. Intermediate fusion is where we process each modality separately into a latent representation or an embedding, and then we fuse them. And then we process this fused representation. Late fusion is when we run each modality through its own model independently, and we fuse the output scores of each modality. Hybrid fusion is a combination of early, intermediate, or late fusion. Each fusion strategy only differs by when we actually fuse the information from the different modalities in the model pipeline. Let's talk a bit more about early fusion. Early fusion refers to combining different modalities at the input level. The advantage of this strategy is that we don't have to perform dedicated processing for each modality. We just fuse them all at the input level and process the fused representation through a single model. One possible application of this is if you have two different sources of the same modality. For example, if you're building a model which predicts positive or negative sentiment of Amazon book reviews, you can utilize the book reviews themselves and also information about the price, author, and genres. A simple text concatenation is enough to consolidate all this information into a single representation, which can then be inputted into the sentiment classification model. The downside to this approach is that the raw input data may not contain rich semantic information. This means that the model is not able to capture complex interactions between the modalities, limiting the benefit the model can derive from the multimodal fusion. How about intermediate fusion? Intermediate fusion is the most widely used fusion strategy. It involves processing each modality into a latent representation, or an embedding. Then we fuse these embeddings and do some final processing to produce the output scores. Autonomous vehicles can use intermediate fusion by integrating data from sensors such as cameras, LiDAR, radar, and GPS. These different modalities cannot be fused directly as in early fusion because they're fundamentally different types of data. But they must be converted into a semantically similar latent representation. And then they can be fused and processed further to predict what the vehicle should do next. The exact process of fusing the latent representations is an implementation detail, but some options include concatenation, element-wise addition, or even attention mechanisms. The advantage of intermediate fusion is the model is able to learn rich interactions between each modality because they are first converted into a machine-understandable representation. The downside to this approach is that individual processing is required for each modality before they can be fused. This may not be a huge issue because of the availability of pre-trained embeddings for images, text, and audio, but it adds extra processing time and can impact inference speed. How about late fusion? Late fusion is more closer to an ensemble model, and an ensemble model is just a group of models which output their own predictions, and then the outputs from each model are used to decide on a final prediction. It's kind of like a voting system. Each modality is processed independently with their own models, and the outputs from these models are then combined at a later stage. An example of using late fusion would be a genre classification system for YouTube videos. Given a link to a YouTube video, One model could process the video content itself and output a predicted genre, and another model could process the transcript or description of the video and output a predicted genre. These two independent predictions can then be aggregated through a weighted average or via another model to produce the final genre prediction. The advantage of late fusion is its simplicity and isolation. Each model gets to learn super rich information on its own modality. The downside is that the system may not be able to learn complex modal interactions, and thus does not benefit directly from the complementary information each modality might offer. Here's an example architecture of a late or intermediate fusion. So you can see we have three different inputs here, which represent the three different modalities which we're working with. Each input is passed through its own unimodal model, and that unimodal model will generate an encoding for that particular modality. Now, this fusion model will take all these encodings and then generate a classification or a prediction. Now, there's a problem that can happen during inference with these multimodal models. These multimodal models are powerful because they can integrate various information sources to gain a comprehensive understanding of the subject matter. But training an ML system on multiple modalities also means that all of these modalities must be available at inference time. However, in some situations, this cannot be guaranteed. Ideally, we would want to design a system which could integrate all available modalities and still function effectively if certain modalities are unavailable. One strategy to accomplish this is by using modality dropout. Modality dropout, or modal dropout, involves randomly dropping or obscuring certain modalities during each training iteration, forcing the model to adapt to varying combinations of modalities. This enables the model to utilize the available modalities so that even if only one of the modalities are available, the model can still produce reasonable predictions. The way we implement modality dropout is a bit nuanced, and I've provided some links in the description box below so you can learn more about how you would implement modality dropout so you can make your models robust to missing modalities at inference time. That was all I had for this video. I hope you learned something new about how multimodal models work and some of the strategies you can use to integrate different modalities into a ML system. Don't forget to check out those links in the description box below. They'll provide a better overview of the details of multimodal models as well as modality dropout. If you like this content, don't forget to smash that like button and subscribe so you stay updated on when I post new videos. With that, I'll end the video here and I'll see you in the next one. Peace.